Let's define lattice planes. Lattice plane is a crystal plane which contains at least three non-collinear points, and these non-collinear points should be single line and should be non-collinear. So, since the lattice is an infinite construction of points and its extended construction of points, mathematically speaking, this lattice planes also contains by definition infinite number of points. So, if it contains at least three non-collinear points, since the lattice can be extended into infinity, the number of lattice points in total would be infinite. So it's a matter of definition. Let's see what, by an example, we have these lattice points. As you can see that a certain plane is defined here with this space contains at least 9 lattice points. So imagine you will extend this space or this plane towards infinity, and this plane which is defined by this shaded region would contain infinite number of lattice points. Similarly, we have another set of planes just behind it, loaded here, correct definition, lattice plane. So again, with lattice plane, different crystal, slightly in a tilted way. So there are 6 lattice points here, contains 99 layer points. So these different directions, oriented on different directions. All these planes, nevertheless, all are lattice planes, or you can call as crystal planes, because they contain at least 3 non-linear points. So it can be, you can draw the same crystal system in the 2-dimensional cubic crystal, and in 2-dimensional you can cut into 2-dimensional structure out of it, or you can look at the crystal into 2 dimension, and this plane clear can be represented in this by these lines in 2-dimensional representation of such a crystal represented, okay, in 2-dimensional of this crystal. Other lines also, planes like you have a plane like this, or you have a plane like this, but if I extend it infinitely into either direction, this is plane which won't get any lattice point. Similarly, this plane won't contain any lattice point. So these 2 planes, these are planes, but these are not lattice planes by definition. So lattice planes, at least 3 lattice points, otherwise they won't be lattice planes. So you should have minimum 3 lattice points. Another more important point is the plane you defined here are visualization tools and not actual things. So they are rather just imaginary objects which you can visualize in a certain 3-dimensional or 2-dimensional lattice, and they are not actual planes which exist within a crystal. So they are a kind of neat understand the arrangement of lattice in a crystal lattice point in a crystal. Technically speaking, lattice plane, the context of lattice is called family of lattice plane. This is called the family of lattice planes. Is a set of equally separated parallel lattice planes which taken together all points of the lattice. So you can see in the definition that you don't have one plane, but rather have a set of many planes aside, and those of set of planes are equidistant from each other. If you combine all these sets, it should be basically contain all the lattice points within the lattice. So imagine such a family, such a set of planes. So all these planes which are shown here are equidistant from each other, and all of them contain lattice points. But the definition of the lattice planes, they form a set such that they are equidistant from each other, and you extend these lattice planes either this direction or in this direction, so that set of lattice planes can be basically cover all the lattice points which in such a lattice up to infinity, so that this would be set of crystal planes, or would be called as a family of lattice planes, and you can take another set of lattice planes. It does not two set of lattice planes. They should not leave out any lattice points, and they should not contain plane without lattice points. So these 2 points are very important. It does not have leave out lattice points, or should not contain plane with no lattice points. And these planes are equidistant from each other, and some of these lattice do contain lattice points, and you extend it either in any direction would cover all the lattice points, but you notice that but they are certainly in this set of planes which does not have any lattice point at all. So this is not a family of lattice planes. You can say set of planes which are equidistant, but there are no planes here of the set which are empty or which does not contain any lattice point, but they do leave out of the certain lattice points. So you can't account for all the lattice points in this lattice. Why this set of lattice planes? So this again not a family of lattice planes. So in this arrangement only, this limit qualifies the technical term of family of lattice planes. How do you represent a family of planes? And there certain index which is used to represent the family of planes called Miller indices or Miller index indices is normally represented by 3 integrals HKL. It's shown in the bracket, and basically you can do is to find the mirror in set of planes, and that indices would be valid for all the planes within the indices. This set of planes would have Miller indices, HKL values, Miller indices. So the Miller indices would have 3 indices HKL. Let's find how this indexing of climbs is done by indexing or family of plane is done. So imagine this set of planes or this representation planes in 2 dimension, so that lines can extend it in a 3 dimension, which is out of the board indefinitely. They won't intersect. These planes intersect 3 axes because they are in the direction of A3, infinitely extended in the direction of A3, certain origin, any point in the lattice. Let's say this one, and you move along first along A1 and see whether set of planes intersect as one axis. Since they are parallel, they don't intersect anywhere, even if you go to infinity. We did the first intersect along infinity. Second 2 is 2 way in this direction, move around output, you can see intersect along A2 at UV distance 1, this lattice, and this one. Third thing is, I'll move another direction along A3, and these planes are extended infinitely along A3, so they don't intersect A3 at all. Again, this is intersect. So the idea 3 intersects along the primitive lattice vectors A1, A2, A3. reciprocal of these intersections, three intersections, infinity, 1 and infinity, you take intersection. Why do you do this inverse? Is something which you will be clear to do in the next model. We can see with us dimension of the reciprocal lattice. So in next model we can see that Miller indices corresponds to the K space, and in K space all the dimensions are in the inverse distances. That's why we are taking the inverse. So you took the intercept, then you look at, once you can took the intercept, you get some numbers, and those numbers you multiply by least common method, LCM. But here you three integers 0, 1 and 0. So you don't have any fraction here. So in order to do that, this is already combination of three number is already your Miller indices. These are called Miller indices. This plane, so 0, 1, 0 is a Miller indices. The resulting combination is Miller indices of 0, 1, 0. So if the intersection is absent, then the corresponding Miller indices 0 seen. So parallel along A1, parallel along A2, A1 and A3 are 0 and A2 is 1. Look at another set of planes and look at, we can calculate the intersections. You move along A1, part of the set of the planes intersects A1 at A distance 1 along A1. Then now you need to do this plane. Just check it, where does it intersects A1 and A2, and you can find out this intersect distance 1 off. This distance is 1 and this distance is off. So it is 1 off. So if this plane is intersected in and is off. First one is 1 and second intersection is off, and third intersection is infinity, because it is extended infinitely towards the third plane is going infinity. So the first one is off 1, the second one is off, and third one is infinity. And when you take inverse of all these intersections, and then you get least common method 1, 2, 0 included. These are 1, 2, 0. These are again Miller indices. Two set of planes. You can see the first plane we have index is 0, 1, 0, and the second one is 1, 2, 0. Okay. Next, go for negative Miller indices. If the intercepts are on the negative side of the coordinate system, then indices get a bar above the number. If it is A1 is 1, and then the second intercept is minus of this plane. You just check it, that one. You can place where this plane is cut along this direction. Negative direction. So from origin it goes in negative direction. This is minus 1 and half, minus of. The third one is infinity. The third one is going in infinity. Infinity. Inverse of this would be infinity. So inverse of this reciprocal, and they take LCM 1, minus 2, 0. Minus 2 can be represented by 2 bar. So 1, minus 2, 0 are Miller indices. Integer. 1, 2, 0. This one is crystal piece. Next one is another set of crystals. A1. See the plane intersect along the axis. So one is 1, minus 2, 0. Another one is 1, 2, 0. So these are the examples for assignment for you. You can find out the Miller indices for all these crystal planes or a set of family of planes. Here, these are the family of planes, and you can have examples or set all the different crystal planes certainly and satisfy the conditions of the family of the planes so that you can find out these Miller indices for the crystal planes. And important property is interplanar distance, Miller indices. The interplanar distance should be same within the same set of planes if they are to be a family, so that you would have 0, 1, 0 set of planes. These are 1, 2, 0. I have this shown here. This is the distance between the interplanar distance here, and this is the interpretation for the 1, 0 plane, and as you might see there, this interpretation is smaller as compared to this one. The general rule, if the lower the indices, the larger the distance between the two adjacent planes of a plane family. So indices is larger and the interplanar distance is small. So the interplanar distance is a small inverse of the index. This because the index is the inverse of distances called universal of intersections. For cubic or simple cubic crystals, the interplanar distance is certain set of planes. It can be cubic is root of a by h square k square plus l square. That is length of the conventional unit cell in a cubic crystal, HKL, root of HKL values corresponding. This is a set of planes, so that valid for the cubic crystals. This is for cubic crystals and not for other crystal systems. So planes in a 3D, three-dimensionals. You need to go for three-dimensional. We have discussed about one dimension. Now we are going for three-dimensional. Instead of line, we are going for now the planes are actually in 3 dimensions, and like this, and this given as A1, A2, A3. This is origin of A1, A2. You can see that intersection is set of distance of A1 unit cell in this direction, A2 intersect all planes, runs parallel to the 2, assuming this planes in the direction is also runs parallel to the 3. 1 infinity. You can inverse it to get a 1, 0, 0 plane. So this is the plane of planar indexes. So these are 3 dimensions. You can extend the planes of 1, 0, 0 plane. How the set of planes will be there, and this is called the family of planes, 1, 0, 0 planes of the crystals extended in 1, 0, 0 into them. Each letter of them add each number of these planes, or 1, 0, 0 planes. Planes. This plane totally the 1, so no intercept, but it cuts into 2 at a distance of 1 or 1, let us constant, and the distance cut along the 3 axis. So intercept is infinity, 1 and infinity. So this is called a plane 0, 1, 0, and this is 3-dimensional equally spaced in, simply given by this lattice. Family of planes will be 0, 1, 0, how this will extend. So, in a simple cubic, along the equidistance is 1, and this is 1, and the intercept along the direction is 1. So, intercept is 1, 1, 1. So, plane will be 1, 1, 1, 1, 1, 1. This is the 1, 1 plane. Intercept is 1 on the plane also. Miller indices are 1, 1, 1 again. So, this is the 3-dimensional set of planes in a 3-dimensional 1, 1, 1. Forms of which one? Family of lattice planes. So, forms where hexagonal, cubic, CC, rhombus, octahedral. See the Y single crystal from geometry. So imagine this is a crystal which are atoms made up of various crystal planes, certain lattice. You cut this crystal into two-dimensional piece out of it. So you can see these lattice points and imagine that this is a cubic crystal. So you have been cutting into certain dimensions. If you go along this direction on the crystal, you end somewhere, and this crystal ends on this plane in this direction, which would correspond to this face here. Similarly, if you go in the other direction, the crystal ends at this plane, this lattice plane, and there should be lattice plane response to your face, which is on the opposite side. Similarly, the other direction, which would be this, corresponds to your face, this one, and opposite side. So look at this plane which corresponds to the crystal where it ends here, corresponds to opposite side. So this plane, these two planes of this plane form of a family of these planes with their own Miller indices, and you can basically label these planes by 100 and 110.